In this video, we'll compare and contrast simple and compound interest, as well as APR and APY. I also would like to give you a few alternate ways to make these calculations so that you have at least two ways to do these problems. Let's look first at the formulas for simple and compound interest. All right, so the compound interest formula was given in your reading. Right, and all of the variables here are defined for you. Capital A represents an accumulated balance after Y years. Some people also think of A as an amount, right? And you may, if you're familiar with financial math terminology, sometimes A is the future value, so you may see FV for that. P is the principal, or the starting amount. That sometimes is also called the present value, so you may see PV. APR is the annual percentage rate. Sometimes you'll see that as just a lowercase r in different contexts. Notice that this is a decimal in this formula, so if your APR is like 4%, then in this formula you would enter that as 0.04. N is the number of compounding periods per year. So some common ones would be monthly and quarterly. It's however often the interest is paid. In like a bank account context, this would be how often you get your dividends. So if those show up on your monthly statements, the compounding period is monthly, and then N would be 12. And if your dividends show up quarterly, then that's 4 times a year, so N would be 4. And then Y is the number of years. Sometimes you'll also see a T for time, but I kind of like Y since it reminds us that the time needs to be in years and not months or days or something like that. Now, one other caution for this formula, the title here says that this is a compound interest formula, but notice what we're actually solving for. It's A, it's the accumulated balance. So that is not just the interest. The A is the interest plus the principal. Right? So there's one other step when you're using this formula. You use this to find the total amount or the future value, and then you need to remember to subtract away the principal, and then whatever's left is the interest. For a simple interest formula, there was not one given in your reading, but I think it's pretty easy to get there. All right, so each year for simple interest, you find the interest by taking the principal and then multiplying it by the APR. Okay, and since interest is not compounding here with simple interest, there is no N to worry about, right? And then you would add that into your amount, and then you would just keep going, and you would sort of repeat this process year after year. All right, so we could do principal times APR over and over again. Like let's say we wanted to find the interest for 3 years, right? Then you would just do this 3 times and add that together, right? And that would be your simple interest for 3 years. The shortcut is to just multiply by however many years you have or however many times you do this. So if we wanted to get a little bit closer to a formula and save ourselves some steps, we can do the principal times the APR to find the interest for 1 year, and then just multiply by Y, the number of years, and then that gives you the interest for however many years you've made an investment or a loan or whatever the case is. All right, and then there's one other thing to do if we wanted. So this is a formula for interest, but if we wanted something that kind of mimics what's going on with this compound interest formula, maybe we're interested in the accumulated balance after Y years, or what A is. All right, so the only thing you need to do there is take what we've just done, which is the interest, and also add in the principal. Okay, so this first part is interest, and then the second part is whatever the initial amount was. Okay, so if you like formulas, you can use that. If you just like more of an algorithm or a step-by-step process, then you could just continue to take, like 5% of your $3,000 investment and then just repeat that for however many years you're earning interest. Okay, so let's make a comparison of simple and compound interest. Now let's just see an example from your reading, and in the reading, this was done using a table to write out all of the different amounts over a 5-year period. So I'm going to modify this slightly and just show you how you can do this with the formulas. If you just want to know the final accumulated balance and you're not interested in seeing each annual amount. Okay, so we're starting with $100 in two accounts that each pay an interest of 10% per year, but one is simple and one is compound. All right, so we have an initial principal of $100. Okay, we have an APR of 10%. And we know it's an APR because it says it's a rate per year. Okay, so that means it's an annual percentage rate. Okay, and then one is simple and one is compound. So for the compound interest, we need the number of times interest compounds per year. And at this point in your reading, we hadn't talked about the n yet. So in this problem, we just assumed that interest compounded once per year. All right, the other thing we need is the number of years for that formula. So what is y? All right, well, we're looking at the growth of each account over a 5-year period. Okay, so 5 is the y. Okay, so let's start with simple interest. All right, so the total accumulated balance is the initial principal, $100, okay, plus all of the interest that accumulates. All right, so each year we're earning 10% of $100, which is 0.1 times 100. All right, so that's per year, and then we're repeating this for 5 years, so times 5. All right, so that's $100, and then 10% of 100 is $10, and $10 for each of 5 years is $50, right? So the total that accumulates after 5 years for the simple interest account is $150. Okay, $100 of that is the principal, and then the $50 represents the interest. All right, what about compound interest? All right, so compound, filling in our formula, we have the principal, right, times 1 plus the APR, and we need the APR expressed as a decimal, so that's 0.10, okay, and then we're dividing that by n, which is 1, so I'm going to skip that part, right, and then the exponent is n times y, right, so that's 1 times 5, or just 5. Okay, if you have a scientific calculator, you should be able to enter this all in at once, right, and I know there's a technology note in your textbook, and you can feel free to use some of the other resources available if you're not sure how your calculator works. But in general, just a couple notes about this. We have 100 times the parentheses, right? So typically you'll need to write a multiplication symbol there. And then you have parentheses, which are needed. Okay, and everything sort of looks the same. You enter it just like you see it. Except for this exponent. So typical exponent keys on a calculator would look like either a little caret, right, or a y to the x key. All right, so look for one of those keys. All right, you can also search for user manuals for your calculator online, or you can just search something like how to enter exponents on TI-83 or whatever the calculator is that you have. Okay, so you do your exponent key, whatever that is, and then the number 5. If you had n times y, like let's say it was 5 times 60 or something like that, you would need to put parentheses around that exponent. So your other option would be to just multiply that ahead of time. So like if you did have 5 times 60, then when you're entering that in your calculator, you could work that out ahead and just enter 300 if you preferred to skip those extra parentheses. Okay, one other option for you, you also can enter this using order of operations, right? That's reviewed in your reading as well, okay? But remember, for order of operations, you want to do parentheses first, then the exponent, and then multiplication, right? So it's a little bit less work sometimes with the parentheses that need to be entered if you do it in steps like this, right? So if you want to do it that way, you would do 1 plus 0.1, and that's the parentheses, okay, and then you would need to hit equals or enter whatever your calculator has. That's important, okay. Then do the exponent, so you would use your little y to the x key or the little caret, and then 5, and then hit equals again. Okay, and then once you've done that, then go back and multiply by 100. And hit equals or enter, and that should give you your answer. Be very careful when you're doing this not to round in the middle of the problem, right? So it's tempting once you get this value for the parentheses raised to the exponent to substitute in some sort of a rounded value at that point, but that will affect the accuracy of your answer, and you can actually be off, depending on the size of the numbers. In some of these financial problems, you can actually be off by even thousands of dollars. So it's best not to round and to try to follow one of those steps, sequences of steps to try to get these answers. Okay, so for this one, you should get 161.05. All right, and it was 15051 on my calculator, but this is the end of the problem, so now you do want to round to the nearest cent, since that makes sense. Okay, so now when we're comparing, remember now that each of these are the final accumulated balance. Not all of this is interest. So we need to take away the principal when we're looking at the interest here, right? So simple interest is $50 and compound interest is $61.05. All right, and as you probably expected by this point, we did earn more with compound interest than we did with simple interest. All right, let's look at an example of compounding that is not annually. So example 5 is monthly compounding. We deposit $5,000, that's the principal, in a bank account that pays an APR of 3% and compounds interest monthly. Okay, so as soon as you see this word compounds and then it tells you how often, that's your clue to tell you what N is. Right, so if it happens monthly, then that's 12 times per year, so N is 12. How much money will you have after 5 years? So the Y is 5. Okay, how much money, that's what we're looking for, and that's the total accumulated balance. So we're trying to find A, and we know all of the rest. All right, so we have principal, 5,000 times 1 plus the APR written as a decimal, so 0.03, okay, divided by N, which is 12, and then the exponent is N times Y, or 12 times 5. Okay, so again, you've got some options for entering this on your calculator. The only thing that's really different here, we didn't talk about what to do when you have a division like this in parentheses, right? And you can just use your division key to represent that fraction bar. All right, so if you wanted to enter this all at once, you would do 5,000, multiplication symbol, parentheses, 1 plus 0.03, okay, division symbol, 12, and your calculator will do order of operations. So by writing it like this, it's going to do this division before it does this addition. All right, so when it does this division, it's making it into a fraction. All right, so that's all taken care of. Close parentheses, and then your exponent key. Again, it might be a little caret or a y to the x. All right, and then now I have two numbers that are in the exponent, so those need to go in parentheses as well. All right, so after that, we would do, I'm running out of space here, but it would be parentheses 12 and then times 5. And then close parentheses. Again, if you wanted to avoid doing those parentheses and the multiplication, you could just work this out ahead and do an exponent of 60. And the answer you get should be 5,808 and 8 cents. Okay, and we'll round here to the nearest cent. I would encourage you to try one of these examples on your own and just make sure that you're getting the same answer as here in the video or in the textbook, and then you just make sure you're comfortable with the way that your calculator works. Okay, let's talk about APR versus APY. So often when you're checking your interest rate for your bank account, many banks don't actually tell you what the APR is. Instead, they'll tell you what the APY is. Right? So the APY is required by law to be reported, whereas you don't necessarily have to report the APR. And that actually works out for us anyway. The APY is, I think, more of an accurate picture of how much you're earning each year, right? So this is the effective yield, okay, or annual percentage yield, and this is just the actual percentage by which a balance increases in 1 year. All right, so all this is doing is kind of evening things out with different compounding periods. All right, so we've seen that if you compound something annually, you don't earn quite as much as if you compound it monthly. And if you compound it monthly, you don't earn quite as much as if you compounded it daily. All right, so the APY takes all of that into account and just gives you a single percentage yield, or it tells you what your increase is. All right, so if the APR is just compounded annually, then the APR is the same as the APY. So it's only when you have like monthly compounding or quarterly where the APY will be greater. All right, so if you want to calculate the APY, you have two options, well, at least two options. All right, one of them is to choose a sample amount for principal and actually work this through with specific numbers. So let's start with that method. Okay, so let's suppose you're depositing $1,000 into an account with an APR of 8%. Okay, so let's find the APY with monthly compounding. Okay, so start with the formula for compound interest, and we'll go through and find the account balance at the end of 1 year. Okay, so notice again, this is annual percentage yield, so we're dealing with just a 1 year period of time. Okay, so we have the principal, right, and times 1 plus the APR, 0.08, divided by n, which is 12, since we're compounding this monthly, and then n times y is 12 times 1, which is just 12. And you're going to find that that's $1,083. Okay, so what we're looking for is the actually a relative change here. Okay, we want to know how much the balance increased, which we started with 1,000 and now we're at 1,083. All right, so we've earned $83 in interest. And then we want to calculate the relative increase, so we want to compare that back to the $1,000 principal. And that gives 0.083, which means that the rate is 8.3%. Okay, so because of the compounding, you're actually getting a little bit more than 8%. So the thing I like about this method is that it just compares this back to something you've already learned, which is how to find a relative increase. Okay, so you take the absolute increase, which is just found by subtraction, and then divide that by the old reference amount that you're comparing to, all right, which was $1,000. The thing I don't like about this is that it's a little bit more work to try to do this every single time. So there is a formula for APY, and the advantage to that is it skips a couple of these steps. Disadvantage is that it's another formula for you to learn. So let me show you that way, and then you can decide which one you like better. All right, so we're just going to mimic what we did here, but skip the numbers. Okay, so what we did is calculate the account balance first. We did that formula, principal times 1 plus APR over n, right, to the n times y, where y was just 1. Okay, so the exponent will just be n, right, and that was the account balance. So that was the $1,083. Next, we found the relative change. And we did that by taking this new account amount, 1,083, and then we subtracted the original principal. Right, so we subtracted P. That gave us $83. And then to get the relative change, we divided that by the original amount, by $1,000. Okay, so that would just be dividing by P. All right, so what happens when you divide this by P? Well, it's actually just going to cancel out the P in each term in the numerator, and it leaves you with the parentheses, 1 plus APR over n to the n. All right, and then P divided by P is 1, so then you subtract 1. All right, so this is a formula for APY, and if you like that and you want to write that down, okay, that will work every time. Notice it doesn't involve the principal at all, which is why we were able to just pick this random $1,000 amount. And you can do the same thing. So if you would rather do this with numbers, then you just choose any old principal at all and work through these steps. Okay, so maybe what you want to do here is use this boxed in formula and substitute in the numbers from this problem, okay, an APR of 8% and where n is 12, and just verify that you do get an APY of 8.3%. All right, let's also talk about continuous compounding, and this is what would happen if the n increased as much as absolutely possible. All right, so continuous compounding means it's more than daily, it's more than every minute, it's greater than every second, it's an infinite number of times per unit of time. All right, so we've sort of glossed over the math of where this number e comes from. And that's because we're dealing with, we're dealing mostly with calculus here. All right, so there is an explanation for what e is and how we know that continuous compounding has this formula. You can search online for this if you would like, something like proof for continuous compounding formula. But the gist is just that if you wanted to verify this without actually proving it, you can just calculate the compound interest with bigger and bigger values for n, and you'll just find that the amount gets really close, the APY gets really, really close to a fixed number. It doesn't actually increase infinitely. And there's a little graph in your reading that shows you this. Right? So you can look at that APY and see that it does increase for a while, and then it sort of levels out at some sort of a set number. Right? So that's why we're seeing the number e here. This is a constant. It's irrational, so its actual true value has a decimal which just continues forever. So this is a rounded value for e. And you have an e key on your calculator. Right? So you can just type in e itself. You can also do e to different exponents, which is what's needed for this problem. Right? So there's usually a little e to the x key. Some people also know a little formula which is PERT, okay, which is p times e to the rt. Okay, so the only difference there is that APR sometimes is referenced by the letter r for rate, and sometimes we use t for time. All right, so if that kind of helps you remember this formula, it's more pronounceable than the one that's given in your text. All right, so let's try an example, and let's go with $100 in an account. So that's P, with an APR of 8% and continuous compounding. Okay, so that's your clue when you see this. If the compounding is continuous, that means there's no way to put a numerical value on n. Okay, n is so large that it's basically infinite, so we can't really plug in a specific value for n. Right, so then that's your clue to switch over to the continuously compounding formula, which doesn't use an n. How much will we have after 10 years? So y is 10. Okay, so using that formula, we have a equals principal times e, right, to the APR, which is 8%, so 0.08, right, times y, which is 10. So simplifying a little bit, this is 100 times e, okay, then hit your exponent key, and then 0.08 times 10 is 0.8. Right, and you should get about $222.55. Right, so this reflects the absolute maximum amount of interest that you can possibly get just by changing the compounding period. Okay, so there are other ways to get more interest. You could bump up your principal, or you could try to get a better APR rate. But if all you're doing is adjusting the compounding period, then this is the most money you can get. We will end with one final example. This is one more thing that you can do with the compound interest formula. We can actually solve for principal instead of for the future value or for a. Okay, so this would be useful if you're trying to answer questions about how much you would need to invest in order to reach some sort of a goal. So let's suppose in this example that we're investing money in an account with an APR of 3%, compounded monthly, so n is 12, and we're planning to leave it in there for the next 18 years. Okay, so y is 18. Why might you leave it for 18 years? Maybe this is some sort of a college investment, so maybe a couple has a child and they want to see how much they can save by the time the child is college aged. How much would they need to deposit now in order to earn $100,000 after 18 years? All right, so the 100,000 is the future value that they're hoping to earn, so that's going to be the A. Okay, two methods for finding this. One is given in your reading. This is example 8, and we can take the compound interest formula and do all of the algebra ahead of time so that we get a formula that looks like P equals, and then we're just working out all of the math on the right side of the equation. Let me give you one alternate way to do this, and that is to just use the formula as written, and we'll do the algebra after we put the numbers in. Okay, so we would have A equals, so I can fill in 100,000. Okay, equals P, since principal is unknown, right, times 1 plus APR, which is 0.03, divided by N, which is 12, and then times raised to the exponent of 12 times 18, N times Y. So let's simplify and do as much arithmetic as we can before we start trying to solve for P. Right, so the left side of the equation is already simplified. It's just a single number. On the right, we can do some arithmetic here, and we'll follow the order of operations. Right, so we need to do the parentheses first, okay, which 1 plus 0.03 divided by 12, and that works out to be 1.0025. Okay, now this worked out nicely with a decimal that terminated. If this was a repeating decimal, or if it continued on for more decimal places, using this method, you're going to be forced to round in the middle of the problem. Right, so the disadvantage with this method is that it's not quite as accurate as doing the algebra ahead of time. But again, if you're not great with algebra and if you don't remember the steps, or if it's confusing to try to work with variables, then this might be a little bit easier to do. Right, so it should work out okay if we just try to keep as many decimal places as possible. But again, the answer might be a little bit off. Okay, so we've done the parentheses. We need to do 12 times 18 next, because that's also a parentheses. It's not written, but the exponent is, it's implied that it's in parentheses. So 12 times 18 is 216. And then there's one more thing we can do. We can do the exponent. So we can take 1.0025 and raise it to the power 216. And here we'll definitely need to round. All right, so that's going to work out to be 1.7148587, and I'm going to do a good number of decimal places. Then the last step to solve for P would be to divide both sides by this long decimal. Okay, so in your calculator you can do 100,000 divided by this number, and hopefully we've kept enough decimal places that the answer for principal isn't too far off from what it should be. All right, so that equals P, and you'll end up with 58,314.11, which actually is accurate. Okay, so to summarize this method, you start out with the formula for compound interest. You go through as much of the arithmetic as possible to simplify, and then you just have one algebra step, which involves dividing both sides of an equation by this number in order to solve for the principal.